Hi, thank you for introduction. My name is Misaki Kojima from Nagoya University in Japan. And I'd like to talk about problem verification, especially starvation freedom, using all-path reachability problem. So let's start with the background. Equivalence verification by transforming a program into a logically constrained term rewrite system, LCDRS in short, is being studied. And to prove equivalence, rewriting induction, RI in short, is used. To use RI, the transformed LCDRS have to be terminating. And verification of non-occurrence of a runtime error, such as race condition and starvation, is expected. And it's expected to verify not only terminating, but also non-terminating programs. So we cannot reduce the verification of non-occurrence of runtime error to equivalence or using RI. And a framework to verify non-occurrence of runtime error using all-path reachability has been proposed already. And this framework works well for race freedom. However, it is not applicable to starvation freedom. So our purpose is to apply the framework to other runtime errors. And we have two results. The first is the modification of LCDRS to reduce starvation freedom to all-path reachability problem. And second is characterization of the normal forms as finitely many constraint terms. So the first topic is about all-path reachability problem. The execution path of transition system is a state transition sequence that is either finite or infinite. And if it is finite, it ends with an irreducible state. And all-path reachability problem, APR problem in short, is a pair of state sets P and Q, and we write P to Q. And this APR problem is valid when every finite execution path starting from a state in P includes a state in Q. And then a logically constrained term rewrite system, LCDRS. And this is computation models for functional and imperative languages. So this is the example, LCDRS for representing factorial calculation, and it consists of 3 rewrite rules. So if you want to calculate the factorial of 3, the calculation starts from a term, fact 3, and it is reduced by these rules. So we get the subfact 3, 1, and reduce the term, and finally we can get the answer 6. And this example is deterministic, but rewriting can be non-deterministic. So LCDRS can represent asynchronous integer transition systems. So this is the example for LCDRS for asynchronous ITS. The example is Peterson's mutual exclusion, and there are 2 processes, process 1 and process 2, and they keep transitioning the 3 states, non-critical states and waiting states and critical section. And they share Boolean variables B1 and B2 and integer variable x. And BI indicates that process I wants to enter the critical section, and X indicates that process X has the priority for the critical section. And this ITS is represented by this 6 rules, LCDRS. The top 3 rules is representing the behavior of the process 1, and the bottom 3 is representing process 2. For example, the process 1 enters the critical section when the process 1 has the priority, x equal 1, or process 2 doesn't want to enter the critical section, so not B2. And this is represented by the second rule. And the initial state of this transition system is this term. Process 1 and process 2 are both in non-critical states, and B1 and B2 is false, and X is 1 or 2. Then all past reachability problems of LCDRS. And the T phi is called constraint term, and where T is a term and phi is a constraint. And this T phi represents the set of ground instance T theta such that theta satisfies phi. And a PR problem of LCDRS is a set of is a pair of constraint terms. So this APR problem is valid when every finite execution path starts from the state in this constraint term, includes a state in this constraint term. And a proof system for validity of these APR problems have been proposed. So next is the reduction of non-occurrence of a runtime error to APR problems. To show non-occurrence of a runtime error, we have to show that any initial execution path doesn't reach an error state. So the reduction method is this. First, we add a rule to reduce any state to a constant success. So this is the term representing any state to success, and we add this rule. And then we add rules to reduce error states to a constant error. So this U representing error states and to error. And we add this rule. And then we reduce the APR problem initial states to success. So the APR problem initial states to success is valid if and only if no initial term reach any error state. Because there are no rewrite rules reducing error to success. So if there are execution path including error, it doesn't reach success. And this is the example to verify race freedom of the same example, Peterson's mutual exclusion. So this is the rule. And first we add a rewrite rule for success. So this term representing any states of this program, and this term to success. And then we add rewrite rules for error states. And term representing race condition is this term, where the process 1 and process 2 are both in critical section. And there are only one error state, so we just add this one rule. And then APR problem to verify race condition, race freedom is this. Initial state to success. So next is the main topic of this presentation, from starvation freedom to APR problem. Starvation is a situation where the process wants to enter but never enters the critical section. So we to know whether starvation happens, we have to look at not only the current state, but also the transition leading up to that state. But the current term representation of states includes no information such a transition. For example, we cannot know whether starvation happened in this stage because there are no information to determine. So the idea to verify starvation freedom is to introduce a counter representing the waiting time. And we consider the starvation freedom of one process, Pi. So the counting starts counting when Pi enters a waiting state, and reset the counter when Pi enters the critical section. And other processes increment the counter when Pi is waiting. And Cmax is upper limit for counter given by user, and the states with C greater than Cmax are considered error states. So to this end, we have to modify the rewrite rules so as to have this counter. And we also have to construct error states as constraint terms. And then we can use the APR framework. So first we modify the rewrite rules of LCDRS. And I used the same example, Peterson's mutual exclusion, and verify the starvation freedom of P1. So first, we have start counting when P1 enters a waiting state. So this is the original rule. And we introduce a counter C. And the C is set to 1 when the process 1 is start waiting. And then we reset the counter when P1 enters the critical section. So this is the original rule, introducing C, and C is set to 0 when process 1 enters the critical section. Then P2 increments the counter when P1 is waiting. So if C is greater or equal to 1, it means process 1 is waiting. So when process 1 is waiting, increment C plus 1. And if P1 is not waiting, so C is less than 1, just keep C. Then we have to represent the error states. As I said before, the state with C is greater than C max, this state is the error state. And this state represents where the counter exceeds some upper limit. And C max is a positive integer given by a user. So is this enough for error states? The answer is no, because the counter is incremented by the other processes. So if all processes are terminating, the counting will stop too. So the error state with this C is greater than C max, it cannot be reached even though their starvation happens. So we have to represent the normal form where all processes are terminating, even though the Pi is waiting for the critical section. So this term, normal forms, and the guard is C is greater than 0. This term is the error states. So how to represent these normal forms. Okay. Then this is the method to representation of normal forms. And we use the same example, Peterson's mutual exclusion. And then first, for each pi and each its state, compute conjunction of negation of guard constraint. So for P1, there are non-crit and weight and crit 3 states. First, non-crit, the guard is P1 prime equal true and X prime equal true. So the negation of this guard is this. But this guard is existentially quantified, so the negation of this guard is just false. And then weight, the guard of this is x equal 1 or not be 2, so the negation of this guard is this. And then crit, the guard is b1 prime equal false. So it's same as the guard of non-crit, so the negation of this guard is false. And the same as at P2, and we can get these 6 pairs. And then construct set constraint terms by cross multiplication. So non-crit and non-crit, non-crit and weight. But we only have to consider the set constraint, so we don't have to consider these false. So only these 2. So the normal form of this LCDRS is this term, where process 1 and 2 are both in waiting states, and the guard is this. So I'll show you how to verify starvation freedom of Peterson's mutual exclusion. So this is the modified LCDRS. So the counter C is introduced, and C is set to 1 when process 1 starts waiting, and reset to 0 when process 1 enters a critical section. And when the process 1 exists from a critical section, you don't have to increment or decrement counter, so C is just C. And then P2 increments the counter when P1 is waiting. Then we add a rewrite rule for success. So it's same. This states representing any states, but don't forget the counter C. And this state to success, we add this rule. Then we add rewrite rules for error states. And there are 2 rules. One is the state where C is greater than C max. And another is the normal form. We add these 2 rules. Then APR problem to verify starvation freedom is same. Initial state to success. So the main result, let R be an LCDRS obtained from an asynchronous ITS, and this be the modified LCDRS to verify starvation freedom. And E be a set of error states. And then APR problem, initial states to success is demonically valid. And then the asynchronous ITS is starvation free. And if the APR problem is not valid, then there exists an execution path reaching an error state. But it doesn't mean that the starvation happened. We just only say maybe starvation happened. because the upper limit of the counter, Cmax, is, if the Cmax is very small, the error state with C is greater than Cmax is can be reached even though no starvation happens. So the remarks, we have implemented the proof system and the transformation. So see this link on the slide. And this tool solved the leading example, Peterson's mutual exclusion, is starvation free in 7.39 seconds. And other experimental results can be seen in our paper. Okay. Then the conclusion, we have two results. First, a modification of LCDRS to reduce starvation freedom to all path reachability problem. And second is characterization of the normal forms as finitely many constraint terms. And we have two future works. One is the development of a disproof method. I said if the API problem is not valid, we cannot say the starvation happens. We can only say maybe happens. So we have to develop a disproof method for starvation. And second is a removal of unfair transitions. We didn't consider fairness or scheduling. So only one process can keep transitioning, but it's not practical. So we have to remove those unfair transitions to verify more practical examples. That's all. Thank you for listening.
Any questions?
Do you have an idea for the future work how such a disproof method could work? Because I have no idea.
We are thinking of where when their execution paths reach to error state, and then we look at the execution path and find same state, like find the loop, and yes. Okay.
Other questions? Okay. Did you think to limit your programs in order to have an exact estimation of the Cmax? Did you think of limit the program that you want to analyze in order to have an exact estimation or more precise estimation of the Cmax? The counter, Cmax.
Is that tied to an aspect of your program? Or is that just a number that the user has to come up with? I think
yeah. If you think to... Okay.
Maybe there is no fixed number or limit, so but we have no idea to find the good Cmax. So that is future work.
Okay. So, other questions? Okay, let's thank the speaker again.